the different tasks are not really compatible with each other, which is a bit strange. So we'll dive into that. Just to take a step back, the reason why we wanted a unified model or foundation model was very much inspired by the case of NLP. And in NLP, it was a couple of years ago, kind of the same situation where you had all those tasks like translation, paraphrasing, sentiment analysis. And all those tasks were tackled independently, or there was very little overlap between the methods. And suddenly came large language models. And large language models, they were able to solve all the tasks very efficiently, and they are very strong because they are generic models, very general, and so it's a higher level of artificial brain if you think about it this way. And in a sense, they can solve all the tasks. And the very important thing is they can solve all the tasks in between. Because suddenly with large language models, you can do translation in a coding paradigm where you can translate in a coding framework to another, or you can do text generation with sentiment analysis. And so you can think of many different applications. And the reason why LLMs are so exciting is because they allow for a very wide range of applications, and they are not only limited to the initial downstream tasks that they were designed for compared to other methods. So in the same spirit, our goal is to have some kind of unified model that can do everything, and hopefully this would enable many applications, and hopefully it will do everything better than existing state-of-the-art dedicated for each task. That's the spirit, but the question is, what should be a foundation model for 3D vision? So for natural language, the question is not so trivial, but at least there's an answer. You have a model that takes as input language and that outputs language. But for 3D vision, as I said before, it could be focal length or depth values or 3D shapes, meshes, normals. It's not so clear what it should be. What is clear to us, at least, is that it should be trained in a weakly supervised manner, at least at first, because we want to be able to leverage very large corpus of data. And so you can't have annotations for billions or tens or 100 billions images. And the other thing for sure is it has to be useful for many downstream tasks. So here I put a list of different words that try to propose answers to what such unified model should be. In our view, such a foundation model should have at least these minimal capabilities to enter the realm of 3D vision. And the first capability is to be able to perform pixel correspondences, like pixel matching, because it's the basis of any multi-view geometry thing. But it should also be able to infer 3D geometry, like in the monocular depth case. You don't have notion of correspondences, but you're still learning priors, learning regularities in the data that you have, such that you're able to do monocular depth. So this is what I would quote from priors, but you can also do that from SFM, learning multi-view priors as well. It should also be able to infer relative pose or the motion, because it's like the root of multi-view geometry is multiple viewpoints that observe the same scene. And part of the problem is recovering those viewpoints. And finally, it should be able to decompose motion or long-term changes, lighting effects, like view-dependent effects. And so with all of this in mind, we wanted to devise a self-supervised training strategy that would learn all of this. And so this is the first work that we did. So this dates back to 4 years ago, I think we started. And it's basically cross-view completion for self-supervised learning. So I'm going to explain what it means. But we set ourselves in the paradigm of MAE, which is self-supervised learning of transformer architectures with masked modeling. So how it works, MAE is very simple. You take an image. You have a VIT that processes it, a vision transformer. So you split the image in a set of batch, and each batch is considered as a token in the transformer architecture. And the training is very much inspired by LLMs. Is you hide a part of the sequence, you hide some tokens in the image, and the job of the architecture is to predict the hidden tokens, just like you would train a network to predict the next word in a sentence. And this is a very strong pre-training strategy, and MAE had very good results on ImageNet, training on ImageNet for semantic tasks like classification or semantic segmentation. And we wanted to do the same thing, basically. So it's the same task for CroCo. We have an input image, and we want to guess what is hidden. So we remove tokens, and we want the network to predict them. But the main difference is now we give the network a second viewpoint. And this is why we call it cross-view completion, because when you see the other view, then you realize that behind the mask on the right, there should be some kind of concrete post. And you can also, as a human, infer its orientation and what it should look like. And how you would do that is by first estimating correspondences. Like you realize this is the same tree. You see they have similar appearances. And so because it's the same tree, you can guess that behind the mask, there is a concrete post. But it's not only copy pasting information, you need to warp the information. And this is dependent on the relative pose. So you need to understand the relative displacement of the camera, of the viewpoint between those two images. But it's not only the camera pose, you need also to estimate some kind of depth information, or in order to warp the information from one view to another, you need some notion of geometry. And not only depth of visible regions, but also priors, like what you probably see the other side of the concrete post that you don't see in the reference view, but you should be able to imagine it. So ideally, if you train a network for this task, it should learn all of this. And finally, obviously, colorimetric adjustment, because the two views might not be taken at the same time of day or even year. So you need to take that into account. Or you could have different color calibration, different exposures, or different senses. And so that's it. So the very simple idea of CroCo is you have a large collection of image pairs, and you train the network to predict hidden regions in one image, having access to another image. And hopefully, if the network is trained properly, it should be able to predict the concrete post. So how do we train this? Actually, it's very similar to MAE. So the upper part that you see here, can you see my mouse? Or...
Yeah.
Okay, perfect. So the upper part is exactly MAE. You have your query image, you patchify it, and you remove tokens, and then you have an encoder and a decoder that are trained to fill the gaps. And this time we have another view, and the way we add this additional information is this view is also going through the same encoder. So it's a Siamese architecture. It's the same encoder, and we just pass two different images. And this time in the decoder, there are cross-attention layers. And these cross-attention layers are basically fetching information from the reference view to the query view that you're supposed to reconstruct. And so I'm not going to give much more details of the architecture. Many different architecture works, by the way. The details are just to push a bit the performance. We train this with a rendering loss, and this is where the self-supervised learning comes in. We don't need so many annotations for the dataset. We just need image pairs, which is just. So this is a rendering loss, and before.
Quick question about this.
Yeah, sure.
So what happened? You require these image pairs to actually have some kind of overlap.
To some extent.
So what happens if they don't? Does it break things, or it just doesn't help?
So when they are, so it's really hard to build millions of image pairs and making sure each of them has at least a small overlap. Some of them have no overlap at all because the way we build the data set, there are some inaccuracies. And it's actually not so much of a problem because in this case, it's just going to do MAE type of learning where it's going to learn to reconstruct the hidden part just based on the context of the query image. But easier said than done, because when we train, actually, we remove, I think, 90% of the tokens. So actually, only 10% of the tokens are visible in the query. But there is a bit of noise in our pairs, but mostly we make sure there is at least a small amount of overlap. but it shouldn't be that much of a problem. And I'm going to talk about that a bit later when I talk about DUSt3R. The fact that there could be no overlap, like no correspondences that you will establish, but still you could learn to transfer information. It's very hard to tell exactly, however, in this case, because this is a pre-training strategy, and I'm going to talk about this later as well. So first of all, I want to show you something. So all the things I've said so far are hypotheses. The network could do something else. It could learn nothing. And so to make sure the network learns something, the first thing we did, actually Jérôme did that, he built this toy example, and we trained the network on this toy data set, which is randomly generated scenes of flying cubes. We call them flying cubes. These are random colors, but always cubes and always the same size. It's just randomly placed. And the task is exactly as I said. You have the reference view and the masked image, and you're trying to reconstruct the hidden region. And bottom left is the prediction of the network, and bottom right is the target, the view that you're trying to predict. And you see when we change the viewpoint of the query image, the cubes seem to be moving as if the network is learning some kind of 3D layout of the scene, the position and the color of each cube. To make sure that the network is really not cheating, we did another experiment. In this case, we switched the scenario. So we are just moving the reference view and not the query view. And I want you to focus on this blue cube here. And you see it's visible in the reference view, so it's appearing in the reconstruction. But when it gets hidden, it disappears from the reconstruction. And so this really tells, it's like an evidence that says the network is fetching information from the reference, and when the information from the reference is not here, then it doesn't appear in the reconstruction. And we have also experiments where you manually change the color of a cube, and it changes the color of the cube in the reconstruction of the corresponding one. So the network, actually, by doing so, we make sure the network is learning what we want it to learn, and it's not cheating. And I think this is a very nice example, because you can train a network in a couple of hours on this kind of examples. You don't need very large compute. You don't need huge cluster. Just in a week and with a small GPU, you can have first results for that. So that's pretty exciting. Of course, we are not limited to flying cubes, and we gather a lot of pre-training data. We started with, yep.
Oh, sorry, I just coughed.
Okay, sorry. So we started with the habitat simulator. So from the flying cubes, we went to synthetic data. These are scenes that were scanned with an RGBD scanner, and then rendered in a habitat simulator. So we have basically synthetic realistic data. This was our first training set in CroCo, and then we added real data in CroCo V2, where we increased the training set, the size of the training set. And as I said, we are in a pre-training paradigm, and just like MAE, we have our pre-trained model, and we fine-tune it on many different downstream tasks. So we started with semantic tasks, as MAE was designed for, but quickly we moved on to geometric tasks, because this is what is interesting to us, 3D vision. And so we started with monocular geometric tasks like monocular depth or edges or normals. And then we moved on to multi-view geometric tasks. And we did, like, at first stereo, binocular stereo and optical flow. And then we did scene coordinate regression and object pose estimation. Scene coordinate regression, it's very important for the next part of this talk. But what I want to say here is we want to keep the architecture as similar as possible to the pre-training, because if you change the architecture, the pre-training becomes useless. So to make the most of it, you keep the largest part of the architecture the same, and you only change the prediction head to adapt to the output that you want. If you want stereo, or if you want monocular depth, or regress poses, then you would just change the prediction head. And this is already a first step towards unification, because we don't have task-specific designs. So it's the same architecture. When we do optical flow, we don't have raft style of architectures, or we don't have 4D correlation volumes or anything. It's just a plain transformer with a decoder that is doing cross attention between views. So that's pretty exciting. I'm just going to show some results about binocular and optical flow, binocular stereo and optical flow. So these are the qualitative results that we get. At the time of submission, we were first on many different benchmarks for optical flow and stereo. I think we are still first on spring stereo, but the others, I think we were beaten, but it's not so important. The important thing is if you don't do CroCo pre-training, you are never going to go anywhere near state-of-the-art on these data sets. And we have clear evidence that CroCo pre-training is making a significant impact on the final performance when you fine-tune it for all your geometric downstream tasks. Just to mention, it's not as efficient on semantic tasks, but it's not what it was designed for, and the training data sets were not so tuned for classification, for example. So that's a bit of the story. The beginning of the story of our project was CroCo. And for us, it was a very nice self-supervised pre-training paradigm where you have a single architecture that can do many different things. And we try to solve many downstream tasks. So gradually, we increased the number of downstream tasks that we were tackling. It's a generic architecture, and it's easily adaptable for many different tasks. The problem is actually nothing is unified yet. You still have a single network for each task. You need to fine-tune it and keep it separate. And so in a sense, the pre-training is learning a general representation, but then you need to fine-tune it for a given application, which is not really practical. You would like to have an off-the-shelf tool that would give you already all the results. But it's not going to be a concatenation of all those models, ideally, because it would be unsatisfying. So in this CroCo story, we looked at the field of 3D vision that I was showing earlier, and there was one task that was still untackled and that was standing out. It's dense 3D reconstruction, and in particular, the unconstrained dense 3D reconstruction, where you have as input a collection of images and no knowledge about the cameras. You don't know where the cameras are, what are their intrinsic parameters, and the goal is to get a 3D model. So we wanted to do this, and if you had to do this as a researcher, you would look into the state of the art and you would pick your favorite tool for that, which would be basically ColMap. It's a very powerful tool, and the pipeline would be two steps. The first step would be to do structure from motion to extract the camera parameters. And once you have the camera parameters for each image in your collection, you would run dense MVS, like for ColMap, I think it's patch match. And you would end up with a dense reconstruction given your observations. And so that is nice. It's extremely powerful. And if you are an expert and if you have many observations and if you're patient, you can end up with industrial quality reconstructions. You have companies that are based on this pipeline. It's extremely efficient, but it's also complex and very brittle. And so if you look at the official restrictions of ColMap, but actually any photogrammetric software, you need images with good texture because you are going to need to establish pixel correspondences for SFM and reconstruction. And so the correspondences, it's a hard problem. It's still a very hard problem, especially if you have blank walls. So you need to have visual support. You also need similar illumination conditions. When you have day and night images, it's much harder to establish pixel correspondences. Same for specularities or transparent surfaces, for example. And the other problem is you also need high visual overlap between your views and at least 3 images that observe each part of the scene. And this is because ColMap is based on the idea of tracks between views. So they are performing pairwise correspondences and then associating those correspondences to have multi-view tracks. And this is the basis of the optimization. And it means you need a lot of high visual overlap, but you also need a lot of different viewpoints, which by design means you need a lot of views. And you need to make sure that the location of the cameras are different, because if you don't have translation, if you have only pure rotation, then it is ill-defined. I will explain that also later. But as you see, the more you dive into the details, the more you realize you need to be kind of an expert to do photogrammetry, and you need a lot of images, and that's a bit frustrating. So in our CroCo mindset, what we wanted, the dream we had was just a non-constrained collection of images. You would have a neural network that would look at them and that would output directly a 3D model. And so this was basically the the endeavor that we started working on last year. And this led to DUSt3R, which we presented at CVPR this year. It's a collaboration with Shuji Wang from the Aalto University and colleagues at Naval Labs. And basically, that's pretty much what I said. It's a neural network that does this, but it's much easier said than done. So something we noticed for dense unconstrained reconstruction is to get the dense model with MVS, you need the camera parameters. And if you look into the SFM pipeline for Colmap, for example, you will notice some kind of paradoxical way of solving the problem. It's understandable, but it's paradoxical because you have your collection of images. You compute, you extract your features, you compute the correspondences, and then you perform geometric verification, which is basically relative pose estimation and filtering the outliers that do not respect the epipolar geometry. So once you have those correspondences, then you have this incremental pipeline where you have, let's say, your current reconstruction, and you add a new frame, you register it, you triangulate the correspondences in 3D, and then you optimize jointly the 3D points and the camera parameters in the bundle adjustment step. And if you do that for every frame, you end up with a sparse reconstruction of your scene with the camera parameters. And I said it's a bit paradoxical because basically, if you want to do 3D reconstruction, you need the camera parameters. But if you want the camera parameters, you need to do 3D reconstruction. And it's a bit frustrating, but it's even more than this, because if you go into the details of this pipeline, even correspondences, establishing correspondences, it's inherently a 3D task. There's, again, this notion of a 3D shape. And so correspondences is pixels that observe the same 3D point. And even if you don't explicitly tell which 3D point it is, there is always this notion of 3D shape. And it's not only the 3D shape, but it's the correspondence between the pixels and the 3D shape. And anywhere from matching to camera parameters to bundle adjustment and then to dense reconstruction, there is a notion of a mapping between 2D pixels and 3D space. Trivially for correspondences, I said it, but for camera parameters, it's a mapping between pixels and rays in 3D space. And if you have a dense 3D model, you could express it as a depth map, which is an explicit mapping between pixels and depth, which is equivalent to pixels to 3D points if you know exactly the camera parameters. So in DUSt3R, we noticed that basically if you successfully predict such a mapping, you're getting rid of all this pipeline, you're shortcutting everything. And so that's exactly what we did. So the mapping we chose the point map. So the point map representation, it's coming from scene coordinate regression, actually. We worked on it before, and this is why we had the idea of using it for dense reconstruction. And basically, it's pretty much like that image. So it's for an image, the point map that is corresponding to this image is exactly the same shape. It's a 2D grid of 3D values, but instead of having RGB values, you have XYZ coordinates. And so really this point map corresponds to a point cloud in 3D, but it also encompasses the correspondence between the pixels and the 3D space, which is the mapping I was mentioning earlier. And this is really the key of DUSt3R. We don't care about the architecture. The important thing is the representation. And so it's a very powerful representation. If you have a neural network that processes point maps, it can learn priors about the geometry of the scene. It can learn priors about right angles or planes or parallel surfaces or the regularities in the shape of the objects of a scene. It could also learn consistency between neighboring pixels, like neighboring pixels that share the same appearance should probably lie somewhere near in the 3D space. And finally, it contains priors about this 2D to 3D relationship, which is actually the camera parameters. I will explain this a bit later as well. So just to mention other works that also do point map or other variations of such mappings, A0 is based on scene coordinate regression as well. And ray diffusion is very similar in spirit, but instead of 3D points, these are plucker coordinates of rays through space for camera parameters. But it's exactly the same concept in these works. So how do we predict such a mapping? We are still in the CroCo framework, so we start from CroCo, but this time we are going to predict 2 point maps, one for each image. And so we had to make another decoder, which is just initialized as the CroCo decoder for the other view. And here I show them as an asymmetric architecture. And basically the decoder of image 1 is going to predict the red point map. And this point map is expressed in the coordinate system of camera 1. So camera 1 is centered and looking in the z direction. And the red point map is basically depth plus focal parameters. And the second decoder is going to predict the blue point map, the point map of camera 2, but this time in the reference frame of camera 1. So it's not exactly doing the same thing because this time the camera 2 can be anywhere in 3D space. It's not centered anymore. And the important thing is both point maps, they live in the same coordinate system. So if you train a network to do that, you take a pair of images and then you predict a pair of point maps that are representing the visible regions of your 2 views in a common reference frame. And we train this in a supervised setting. So we have ground truth information, we have ground truth point maps, and we have a scale invariant regression loss. And we very simply train the network to predict point maps. And that's it. And so this notion of mapping, in hindsight, we realized that not only does it represent the 3D shape, but it also represents the camera parameters. And from the point maps, you can extract the camera calibration. So in this case, we consider only the focal length. You can also extract the depth, as I was mentioning earlier, and you can do depth in monocular and multi-view settings. That's starting to get exciting because from the point map, you see you're kind of solving many different tasks or downstream tasks of 3D vision in a single prediction. Same, you can establish pixel correspondences just by fetching nearest neighbors in 3D space between your 2 point maps. And finally, you can do camera pose estimation. Very simply, you can do it in many different ways, but here you see you have the calibration and the pixel correspondences and 3D points. And so you can do PNP or essential matrix or whatever. There are at least 3 different ways of getting camera poses. You can do that in the pairwise case, but you can also do that in the multi-view case, and you can also do visual localization. And finally, you also do 3D reconstruction, which was the point of all this thing. And so here we're starting to get much better unification in terms of model because we have a single model that does everything, well, all those things at least. So again, we train this on a large corpus of data. Half of it is coming from the CroCo pre-training, actually, where we had camera parameters and depth information. The important information I want to mention is, as a rule of thumb, we try to have 50% of synthetic data and 50% of real data to learn perfect priors on synthetic and then scene to real, closing the scene to real gap by learning on real data. So with DUSt3R, as I said, you have a network that looks at a pair of images and that predicts a pair of point maps from which we can recover the camera parameters. And this is exactly what it looks like. This is the colored point cloud of the 2 point maps visualized. This is the raw prediction. I mentioned you can do monocular depth, but you can do monocular reconstruction in general. If you have a single image, you just feed it twice to the network, and then you end up with a monocular 3D reconstruction and camera estimation. In this case, the camera is centered, so there is no notion of extrinsic parameters, but you can extract the focal length from this prediction, which is a step towards auto-calibration. And it's very useful to have this focal estimation just from the raw images. Now the question is, what happens if you have more than two views? What we did in DUSt3R is this global alignment where you basically do every pairwise comparison and then you align all the predictions to live in the same coordinate system. So in a sense, it's kind of a bundle adjustment where you are optimizing for 3 points in camera parameters. But this time the loss is in 3D, it's not a reprojection loss, and it's very well behaved. It converges really fast if you don't have too many images. So yeah, that's pretty neat. With DUSt3R, we have a model that works indoors, outdoors, on many different kind of scenes and objects. And we started pushing the boundaries a bit, and we had in our data set some pairs where the views were opposite, like on this motorcycle. And you can see the network is predicting the two cameras facing each other, and it's basically reconstructing the two sides of the motorbike, which was, I would say, surprising, because usually you would rely on pixel correspondences, but in this case you have maybe this portion that you see is in common, but the rest, it's really, there is no notion of correspondences. So the network here is heavily relying on monocular priors and also generic 3D priors about the shape of a motorcycle and the most likely outcome of these observations. So this was very nice to have such behaviors, and we wanted to push the limits even further with what we call the impossible matching scenario, where you have two views where we made sure there was no overlap. And this is on the right, the prediction. So these are two views of Jerome's office. And on the right, you see the prediction, and you see there is clearly no overlap, but you still have a dense reconstruction with the camera locations and parameters. So yeah, I had trouble sleeping last year when we were having these first results. It's very exciting. Everything is nice. We do a lot of evaluations on all the tasks I mentioned earlier. So now I'm just going to talk about limitations a bit, because we are a bit short on time and I have many other things to say. But basically, DUSt3R is extremely robust, but it lacks accuracy. And it lacks accuracy mostly because it's based on regression. And if you look at multi-view stereo reconstruction on the DTU dataset, you can see the overall distance is the chamfer distance in millimeters. So for the DTU dataset, we have 1.7 average chamfer distance without considering the camera parameters as given. We just look at the images, and this is the accuracy that we get after aligning our prediction to the ground truth. And I would say 1.7 millimeters, it's rather reasonable, but it's very far from state of the art on these datasets. Something else we noticed is, let's say for visual localization, for example, you have different ways of estimating the camera parameters. As I was saying earlier, you can establish pixel correspondences by nearest neighbors in 3D space, and then you do PNP on the known map that you are given in visual localization. Or you can do directly PNP on your prediction if you align your prediction to the given map. And the sad story is, all the time, pixel correspondences give better quantitative performance. And we've seen that in many instances. And so it was nice. We could have better results by doing this with DUSt3R. But the problem is DUSt3R was not trained at all for matching. It is a regression task. So very naturally, the next question was simply, what if we did? And so this leads us to the last part of this presentation, which is, yep.
Quick question, Vincent, sorry, before we move on. So
Yep.
I was just wondering about, we actually discussed your paper a couple of weeks ago in the seminar with another speaker. I was just wondering about scale.
Yep.
So are the predictions up to scale, or can you trust the scale of the predictions?
So for DUSt3R, I said we have a scale invariant loss. So during training, when when we do our prediction, we align the prediction to the ground truth with the scaling, the optimal scaling. And so with DUSt3R, you have no guarantee on the scale. But with MASt3R, we realized very much like monocular depth, you can do metric monocular depth. Actually, you can do metric binocular point map predictions pretty much the same way. You just change the loss such that the scale is taken into account when you know the training data is metric, obviously. And so for MASt3R, we have metric predictions. I would say as metric as possible, and it's inherently limited by the training data that you have. So I'm going to explain that a bit later, but we are going into this exactly right now. So MASt3R, it's I would say not a groundbreaking idea. We just take DUSt3R and we give it the ability of performing pixel correspondences. And so how we train this is we have an additional head that is predicting local features. And then we are going to train those local features not with a regression loss that we had before for point maps, but now with a contrastive loss. So info and CE in our case, I guess other losses would also work. The point here is you want to have local features that correspond to be close and local features that do not correspond to be far apart in descriptor space. And this is, we have ground truth information for that, and we train it with an info and CE, which is now based on a classification loss and not a regression loss. And also for MASt3R, as I was mentioning, we make the point maps metric. It's kind of a detail because you could get the scale from other sensors or from other data or from other models. But it's nice to have a generic model that also gives you an approximation of the scale. And so it's trivial to do it. You just have a regression loss and no longer a scale invariant regression loss. And so just to mention, many of our data sets, we built the ground truth with ColMap or other SFM pipelines. And for those, the scale is unknown. So the reconstruction is at an unknown scale. And in this case, we still use them for supervision, but we use the scale invariant loss in this scenario. So it's like a hybrid loss depending on the data set. So again, with MASt3R, we try to solve as many tasks as possible, but because we were doing pixel correspondences, we focused on tasks that were interesting for pixel correspondences. So map-free localization was one, relative pose, obviously, visualization, visual localization as well, and multi-view reconstruction. And here I'm just going to talk about map-free and multi-view reconstruction for the sake of time, but you can check the paper for more experiments. So let's start with map-free. So basically, map-free, it's a challenge where you need to estimate the relative pose between two images. But the problem here is that the translation part of this relative pose has to be metric. And it's one of the motivations of having MASt3R metric is exactly because we wanted to solve this task. And so we needed some idea of the scale of the scene because pixel correspondences alone are not sufficient. With pixel correspondences, you only get the relative transformation up to an unknown scale. And the previous methods for this were using regular correspondences for relative pose and metric monocular depth with like DPT for scale for each view. Something else that is extremely nice about this dataset is in many cases, you have this very challenging scenario where as a human, you have pretty much a hard time guessing what's the relative displacement between the views. It seems like there is no notion of correspondences here. And actually, if you ask MASt3R what is the viewpoint change, it will tell you that the post you see on the left is the pole you see on the right here, and actually the views are facing each other, which is nice because it means MASt3R is basically as robust as DUSt3R. It can handle extreme viewpoint changes. But you have pixel correspondences. And as I said earlier, pixel correspondences give you better quantitative performance, so much better than when we submitted to this benchmark. The authors thought we were basically cheating and trolling them by putting a fake submission on the benchmark. So now they believe that we did not cheat, and I can confirm that we did not cheat. We just trained on the training data set they provided, and then we had these results on the test set, which is for which we don't have the annotations. It's a public online benchmark where you submit your results. So we could, okay, that's enough. Fun story again, they decreased the threshold after we submitted master because we were close to saturating the previous one. Just a quick explanation, this VCRE, it's a reprojection error of 3D points in the scene based on the camera parameters, the camera locations that you estimated, extrinsics basically. And this is translation and rotation error in meters and in degrees. So just from a pair of images, having an average error of 35 centimeters, I think it's very reasonable considering the difficulty of the task. We were first on the map-free localization challenge at ECCV, and I think we are still first on the benchmark and first by a significant margin. So that's pretty exciting. But there is still a lot of room for improvement if you look at the results. In many scenarios, in many cases, we lose the tracking. We don't know where the camera is basically. So there is still a lot of room to be gained, a lot of performance to be gained. So to finish quickly on the MBS tasks, I was showing results earlier with regression. So this is the results we get with pixel correspondences. And so very simply, we take image pairs, we establish correspondences, and then we triangulate everything in 3D. And this is the results that we get. And it's very important to say that, again, there is no task-specific design. We did not train for MBS, we trained for point maps and correspondences. And this is the byproduct where you just triangulate given your camera parameters. And quantitatively speaking, again, you can see that matching is far superior to regression, like having pixel accuracy, like pixel perfect accuracy, or even sub-pixel accuracy. If you do triangulation with many views, it's obviously going to be much better than direct regression. And in this case, we go from 1.7 millimeters in overall chamfer distance, average chamfer distance, to 0.37 millimeters, which is obviously much better. But interestingly, it's getting much closer to state of the art on this data set. And even more interesting is all those methods are learning based and they are trained on the DTU dataset. And the thing in the DTU dataset, it's a robotic arm for each scene that places the camera always in the same location. And so in our case, we don't train on this dataset, so we can argue that we've never seen this camera setup before, and hopefully we are not overfitting to this scenario. So really, these results are showing that we have very good generalization capabilities and that we can test on many different scenarios. So just to finish, I will just talk about other works that are based on DUSt3R and MASt3R. In our endeavor to solve all the tasks of 3D vision, one that remains is novel view synthesis, and luckily other people did that for us. Well, they were not working for us, but they did that, which is nice. Instance plat came a couple months after the release of DUSt3R, and instance plat is basically using DUSt3R as initialization for camera poses and 3D points of the scene in a sparse view setup. And then you optimize 3D Gaussians for novel view synthesis. And the result is from 3 views in 20 seconds, you can get such renderings, which is really, for me, it's opening new applications and new capabilities to existing systems. So that's pretty neat. Just to mention also, Splatter is a derivation of DUSt3R, where they have an additional prediction head to predict Gaussian parameters. And so in a single forward, without optimization, you end up with a set of Gaussian splats that you can use for novel view synthesis. In a different direction, Spanner is a work that is attacking the problem of multi-view predictions. And so if you remember for DUSt3R, when we have multiple views, we do these pairwise predictions, and then we do the global alignment to have everything living in the same coordinate system. And what Spanner is doing is a system of spatial memory where for each incoming view, you predict the point map of this view in a global reference frame. And then you add the view to your memory, and then you take the next view and you predict it again in the same coordinate system, which means in a single forward for each image, in a single forward of your network, you end up with a point map in a common reference frame, and you don't need to do any global alignment, which is very nice. And this is giving this kind of incremental reconstruction where you have nice frames, nice FPS. We tried it. I don't know how they get 50 frames per second. We are more close to 10 to 20, which is already pretty nice. That's something very interesting. Last thing is Monster, and Monster is basically training DUSt3R for dynamic scenes, and you can just from an input video get these kind of renderings where you have a point map of the rigid part of the scene and a segmentation mask for the dynamic parts, and this allows you to replay moving objects or persons in the scene with a moving camera, and this is really showing the capabilities not of DUSt3R but of the point map representation, because the point map is a relaxation of the standard camera model, and it allows you to model impossible camera configurations, but it also allows you to model motion, for example. And this is something we had in mind. Obviously, we didn't have time to do it, and they did it, so that's perfect. And yeah, really the results are speaking for themselves. When I started my PhD, I was dreaming of a system that would do that. So yeah, that's pretty neat again. So in conclusion, all our code is available. I think you might already have seen it. We did master SFM, which is how to do global alignment on many images, on large image collections like this one. It can be as large as 1,000 images. It fits in memory. And yeah, basically you have this demo where you can drag and drop your images and you get your 3D scene and your camera parameters. So focal length, camera poses, as metric as possible, metric geometry as well, and also correspondences. If you want to have very high accuracy, you can extract matches. And yep, that's pretty much the end of the story. Or is it? Yep, I'm done.
All right. I have to run, but maybe I can ask one very quick question. So the thing that I was confused about was, what are the requirements for the real world data for the training of DUSt3R? You just need RGBD, and that's sufficient to calculate those like relative correspondences between camera frames?
So, okay, so it depends. What we have for training is usually depth plus camera parameters so that you can build the point maps. And from the point maps, we get the correspondences to supervise master. Then if you're talking about dynamic scenes, you would need dynamic point maps, and it's not so easily to come by. In Monster, I don't remember exactly which datasets they used, but they have annotations of depth plus camera poses on these scenes, and this is how they supervise it, I think. I'm not sure. But okay, you can have many different sources. So in our case, we have synthetic data where you have everything you want. You have also sparse depth from LiDAR if you have LiDAR scans that are aligned to your cameras. So in this case, you know the camera parameters and you know sparse points, and you can supervise with a sparse loss. It also works. Same for correspondences. You can have sparse correspondences and it also works. And we also have RGBD sensors like time of flight, Kinect, structured light scanners, basically all the data that we could find. And ideally, it should be as accurate as possible because it's going to be very important for the visual quality and the quality of the overall prediction.
Makes sense. Okay, yep. Thanks. I got a roll.
I'm just curious, do you have some like particular scenes or scenarios on which your models don't perform well just because they were not in the train set? They're kind of
Yep.
OE and doesn't work too.
Yeah. So obviously, yes. So the point map representation, you can represent any camera model, I guess. But the thing is, in our training, we only have pinhole camera models. And so it means if you try with fisheye cameras or orthographic, like satellite images or panoramic images, then suddenly the camera model is different. And so the predictions are not as reliable as the ones you could have with a pinhole camera model. And this is due to the training data. And most of the limitations will actually come from the training data because we make very little assumptions in the design of the network and the use of the point maps, basically. The other failure case is when you observe something that was not represented in your training data, and typically for DUSt3R and MASt3R, we have no human data or almost no human data. And so these kind of scenes, it's completely, well, it fails or it gracefully fails, I would say, most of the time, but it's still failing. Like the humans are not well reconstructed, sometimes they are not reconstructed at all. And this is again due to the training data.
I see. Okay. No questions. Okay, maybe I have another one. So in cases where the correspondences are ambiguous, so you gave this example of like the stop sign, I think, or the post, and it managed to like
Yep.
give you a reasonable match. But I'm just wondering if you had like multiple posts like that in the scene, maybe there could be like different possible matches or different point maps that could be reasonable. Do you currently have a way to kind of sample a distribution over reasonable point maps, or right now it's just like a one prediction, one time?
That's a great question. So it's in our case we do regression. So you're predicting the mean of the distribution of the possible outcomes. One other way would be to have diffusion. And actually, the first prototype that we made was using diffusion. And so with diffusion, you're able to sample possible outcomes. So you start from random noise and you gradually converge towards a set of point maps that explain the observation. And if you change the noise, then you will change the predictions. And so this way you could sample different modes of the output depending on the ambiguity. And you could also measure the ambiguity by just looking at the variance of your predictions.
Right.
But in the end, we didn't do that because it was already complicated enough. And training the network without diffusion, it's already taking, I would say, overall roughly 10 days. And with diffusion, we didn't do it until the end, but it's at least 5 to 10 times slower. So we would need more compute or more patience. It makes everything more complicated. Usually, we like to iterate very quickly on the designs and on the different ablations. And if you have a network that trains in 10 days, then it's not optimal. So for us, it was the first step to do regression, but you can do diffusion for sure. We did it, and it also works. But then we don't have the same results and evaluations to go with.
Okay. All right. That's it for me. Okay. Thank you, Vincent. Merci beaucoup.
Yep, you're welcome.
Great talk. Really enjoyed it.
Thanks.
And sorry again about the recording thing.